Hello, in the previous clip we initiated discussion on non-minimum phase systems and tried to look at how non-minimum phase systems could potentially pose challenges to us as control engineers. And we took some case studies, we took some specific numerical examples through which we showed that in the presence of a time delay, for instance, our abilities as control engineers gets drastically diminished, and we often have to settle for closed loop systems with extremely low closed loop bandwidth in order to make sure that the closed loop system is stable in the presence of the non-minimum phase term such as a time delay. Now we shall, in this clip we shall continue this discussion. We shall first briefly look at non-minimum phase systems which have right half plane zeros, and subsequently look at the fundamental limitations on the gain crossover frequency and the phase crossover frequency that are imposed by the non-minimum phase terms. Again we will first do this for the case of the right half plane zeros and repeat the same exercise for the case of time delay. Subsequently we will look at the fundamental limitations that are imposed on the achievable loop gain at frequencies below the gain crossover frequency as the result of the fact that there exists such a thing as the maximum achievable gain crossover frequency. So let us first get started with non-minimum phase systems which have right half plane zeros. As we discussed in the previous clip, the general transfer function for a plant P of S which has a single right half plane zero at S is equal to A is given by P of S is equal to A minus S times P1 of S, where P1 of S is assumed to be a transfer function all of whose poles and zeros are on the left half of the complex plane. So this term is the non-minimum phase term, and for the sake of greater clarity in understanding the effect of this term, we shall rewrite this expression by multiplying the right hand side and dividing it by the term A plus S, so that on the right hand side we would have A minus S by A plus S times P1 times S, P1 of S times A plus S. So I have done nothing but multiply and divide the right hand side by the same term, namely A plus S, and I shall call the product of P1 and A plus S as the minimum phase part of the transfer function. So I shall give it a special name as PMP of S. So P1 times A plus S shall be called P minimum phase of S, and that gets multiplied with A minus S by A plus S to give me the actual transfer function of the plant P of S, which once again I shall relabel as PNMP of S to highlight the fact that we are now talking of a non-minimum phase plant. So the non-minimum phase plant can be written as a product of a term of this kind, namely A minus S by A plus S times a minimum phase transfer function PMP of S. Now this particular term has a special name, it is called as a Blaschke product, BLASCHKE product. So to understand the effect of this Blaschke product on the overall magnitude and phase characteristics of the non-minimum phase plant, let us first draw the Bode plot of the Blaschke product alone. So to draw the Bode plot of the Blaschke product, we set S is equal to j omega, in which case the Blaschke product is going to be given by A minus j omega by A plus j omega. So the magnitude of the Blaschke product is going to be equal to square root of A square plus omega square divided by square root of A square plus omega square once again, and is going to be equal to 1. So you note in this case a similarity in the magnitude of the Blaschke product with that of the time delay. So once again this particular term does not modify the magnitude characteristics of the minimum phase plant in any particular way. Its gain is going to be 1 at all frequencies. However, if we compute the phase of the Blaschke product, we note that in the numerator we have A minus j omega. So, the phase associated with that would be minus of tan inverse of omega by A, and then we have a denominator of the kind A plus j omega, and the phase of A plus j omega is going to be equal to tan inverse of omega by A, and since it appears in the denominator, it is going to be minus of this particular value, or in other words minus of tan inverse omega by A, and hence the net phase of B as function of frequency is given by minus 2 times tan inverse omega by A. So, let us now, having derived the magnitude and the phase characteristics of the Blaschke product, let us now graph its Bode plot. So, the magnitude plot, where the x axis is log omega and the y axis is 20 log of magnitude of B, will be essentially a horizontal straight line that is coincident with the x axis of the plot, because the gain of the Blaschke product at all frequencies is going to be equal to 0 dB, or in linear terms it is going to be equal to 1. Now, as far as the phase is concerned, once again the x axis will be log omega and the y axis will be the angle of the Blaschke product. We note that when omega is much less than A, then the angle of the Blaschke product is going to be approximately equal to 0, and when omega is exactly equal to A, we would have tan inverse of omega by A to be equal to tan inverse of 1, which is equal to pi by 4, and hence the angle of B is going to be equal to minus 2 times pi by 4, which is minus pi by 2. So, angle of B is going to be equal to minus pi by 2 at omega equal to A. Now, in the limit that omega tends to infinity, or when omega is much greater than A, we note that the term tan inverse of omega by A will tend to tan inverse of infinity, which is pi by 2, and hence the angle of B will tend to minus 2 times pi by 2, or in other words minus pi. So, by making note of the angle of B at these 3 particular limits of omega, we can now draw a rough phase characteristic for the Blaschke product. So, if I were to mark out the point A on the Bode plot, we note that at the location omega equal to A, the phase lag is going to be minus pi by 2, and for frequencies much less than A, the phase lag is going to be close to 0. So, the phase is going to decrease in this particular manner. It is going to reach minus pi by 2 at omega equal to A, and then it is going to continue decreasing as omega tends to infinity, and it is going to asymptotically approach the angle minus pi. So, as omega tends to infinity, the phase lag will tend to minus pi, but it will never cross the line minus pi. So, this is the phase characteristic of the Blaschke product, and you can immediately see that this phase characteristic once again adds an extra phase lag to the overall phase characteristics of the minimum phase part of the plant, namely P_mp of S, without affecting its magnitude characteristics. So, in that respect, therefore, it does something similar to what a time delay does to the overall system. Even in case of the time delay, we have no modification of the magnitude characteristics of the minimum phase part of the plant. It is just that the phase lag gets increased by an amount omega times capital T, where the capital T is the time delay, and in this case where we have a non-minimum phase 0, we note that once again the magnitude characteristic remains unaffected. So, the magnitude characteristics of P minimum phase is going to be equal to the magnitude characteristics of P non-minimum phase. However, the phase characteristics of P non-minimum phase is going to have an extra phase lag compared to that of the phase characteristics of P minimum phase by the amount given by minus 2 tan inverse omega by A. And once again we see that since the phase lag goes from 0 to minus pi, this term, the Blaschke product, forces a plant to undergo phase crossover. So, if we have a first order plant, for instance, if P minimum phase is a first order system, then ordinarily this system would not have a phase crossover frequency at all, because the phase goes from 0 to minus pi by 2. However, if we were to cascade such a first order minimum phase plant with the Blaschke product, there will be a particular frequency at which the phase will cross over, and hence we will have to start to worry about the stability of the closed loop system even when we are using fairly simple controllers such as a proportional controller. So the problems that a non-minimum phase term, a non-minimum phase 0 causes for stability has very close parallels with the kind of problems that we encountered in the case of the time delay. So I shall not take extra numerical examples to underscore the problems that this particular term would cause, because the magnitude and the phase characteristics of this term have certain parallels with the magnitude and phase characteristics of the time delay, and hence one can easily predict and anticipate the kind of problems that this particular kind of phase characteristic, where the phase lag goes from 0 to pi, will cause to a closed loop system. The problem stems essentially from the fact that this kind of a phase lag forces the open loop system to have a phase crossover frequency that is much less than the natural phase crossover frequency of the minimum phase part of the plant itself. Now both the non-minimum phase 0 as well as time delay, as we discussed, impose certain fundamental limitations on our abilities as control engineers. So let us now see how one can derive these fundamental limits that are imposed by these terms. And I want to underscore at the outset that the gain phase relationship that was discovered by H.W. Bode plays a central role in coming up with the approximate expression for the fundamental limitations that we would be talking about in connection with these non-minimum phase terms. So what I shall do next is to draw the Bode plot of a general open loop system which has a non-minimum phase 0 in it. So the magnitude plot will have 20 log magnitude of L plotted versus log of omega, and let me assume that the magnitude plot does something at low frequencies. So depending on the poles and zeros of the open loop system, the magnitude might reduce or increase and so on and so forth. So I shall not draw its exact characteristics. The exact characteristics are of course dependent on the structure of the plant as well as the controller that we are using, but no matter what it does, there needs to be a particular frequency at which the gain will cross over, because the plant's gain will reduce and the controller's gain will also reduce beyond a certain frequency. There will be a certain frequency omega gc, the gain crossover frequency, at which point the magnitude crosses over from some value above 0 dB to some value less than 0 dB. Now I shall also draw the phase characteristics associated with the corresponding magnitude characteristics. So I have drawn the line theta equal to minus pi as the dashed line here. So at very low frequencies the phase does something, and then I shall once again not draw the exact phase characteristics at very low frequencies, because it once again depends on the exact structure of the plant and the controller. Now near the frequency omega gc, let us say there is a certain phase margin. So at the frequency omega gc, the phase lag is such that it gives us a certain phase margin Pm, and then the phase continues to decrease and finally crosses over at some frequency omega Pc. So let us say this is the phase characteristic and this is the general magnitude characteristic. Now in the vicinity of the frequency omega gc, let us assume that the slope of the magnitude characteristic is minus 40 alpha decibels per decade. So let us say that the poles and zeros of the plant and the controller are such that we get a slope of minus 40 alpha decibels per decade near the gain crossover frequency. Now the first point I wish to make in connection with the Bode plot, the general Bode plot of a non-minimum phase loop gain that I have drawn here, is that if we were to define LNMP as the non-minimum phase loop gain, which is going to be equal to the controller times the plant PNMP, then we can write LNMP as being equal to C times A minus S by A plus S times P minimum phase Now assuming that our controller is also a minimum phase controller, then we can lump the terms C and P minimum phase and write that as A minus S by A plus S times L minimum phase. So in other words, L non-minimum phase can be related to L minimum phase, which is defined as C times P minimum phase by the expression that has been shown here. It is equal to the Blaschke product times the transfer function L minimum phase. Now I want to first point out that the magnitude characteristics of L non-minimum phase, which is what has been plotted at the top there, is going to be exactly identical to the magnitude characteristics of L minimum phase. That is because the Blaschke product has a gain of 1 at all frequencies. However, the phase lag of non-minimum L non-minimum phase, that is the angle of L NMP, is going to be equal to the angle of the Blaschke product, which is A minus j omega, angle of A minus j omega by A plus j omega, plus the angle of L minimum phase. Hence the angle of L non-minimum phase is going to be equal to minus 2 times tan inverse of omega by A, as we discovered in our previous slide, plus the angle of L minimum phase. Now let us apply this particular equation at the gain crossover frequency. Now at the gain crossover frequency, we note that our phase of the non-minimum phase loop gain is going to be given by minus pi plus the phase margin. So suppose I have specified a certain phase margin, then the angle of L non-minimum phase at the gain crossover frequency by definition is going to be equal to minus pi plus Pm, and that is going to be equal to minus 2 times tan inverse of omega Gc by A plus the angle of L minimum phase. Now we can make another important simplification to the equation that I have written here. We note that if our magnitude characteristic is rolling off at minus 40 alpha decibels per decade, so the magnitude characteristic, I want to remind you, corresponds to both that of the non-minimum phase loop gain as well as the minimum phase loop gain. They both have the same magnitude characteristic. So this minus 40 alpha decibels per decade also happens to be the magnitude characteristic of the minimum phase loop gain L MP. Now if we have a minimum phase loop gain L MP whose magnitude is reducing at the rate of minus 40 alpha decibels per decade, then Bode's gain phase relationship, which is applicable to minimum phase loop gains, tells us that the angle associated with this roll off, which is the angle of L MP, is going to be approximately equal to minus alpha pi. So this we get from Bode's gain phase relationship, which tells us that the phase characteristics at any particular frequency is determined approximately almost entirely by the slope of the magnitude characteristic in the vicinity of that particular frequency. So since the slope in the vicinity of omega Gc is minus 40 alpha decibels per decade, the angle of L minimum phase is approximately going to be equal to minus alpha pi. Now if we substitute this into this equation, we would have that the phase of the non-minimum phase loop gain, which is minus pi plus Pm, is going to be equal to minus 2 tan inverse omega Gc by A minus alpha pi. Now if we rearrange this equation, we would have that pi times 1 minus alpha minus Pm is going to be equal to 2 times tan inverse omega Gc by A, or in other words omega Gc by A is going to be equal to tan of pi times 1 minus alpha minus Pm whole divided by 2. Now by simplifying this further, we would note that the expression on the right hand side is going to be equal to cot of alpha pi plus Pm divided by 2. So, our gain crossover frequency is related to the location of our non-minimum phase 0 A and the specified phase margin Pm and the roll off near the gain crossover frequency alpha according to the equation that we have given here. Now, this is an important equation because it allows us to work out the best possible or the highest possible gain crossover frequency. Why is that so? That is so because we note that for any variable theta, the function cot theta is a decreasing function of theta. So, cot theta assumes its maximum value at theta equal to 0, at which point it is equal to infinity, and as theta tends to pi by 2, cot theta will tend to 0 monotonically. Hence, for the gain crossover frequency to be a maximum, we should have the term within the square brackets, namely alpha pi plus Pm by 2 to be as small as possible. So, the smaller the term alpha pi plus Pm by 2 is, the larger will be the term on the left hand side, namely omega Gc by A. Since A is a constant, that will automatically mean that omega Gc will get maximized. Now, if we focus on the term within the square bracket, namely alpha pi plus Pm by 2, we note that the phase margin is something that we might have specified. We want, in the interest of stability, our open loop system to have a certain phase margin. So, we cannot play around with the term Pm. All that is left with for us to play around with is the term alpha. So, the smaller the value of alpha, the higher will be the gain crossover frequency, and we desire a fairly high gain crossover frequency so that our closed loop bandwidth can be adequately high, and with that high closed loop bandwidth we will be able to reject a large range of disturbances or track a large range of references. That is the purpose behind our objective to maximize omega Gc. So, the smaller the value of alpha, the larger will be the value of omega Gc, and the question now is, what is the smallest permissible value of alpha? To answer this question, we need to focus on the magnitude characteristic near the gain crossover frequency, since by definition we note that we have the magnitude characteristic crossing over at omega Gc. Our alpha here has to necessarily be some positive value. If alpha is a negative value, then it means that the slope near the gain crossover frequency is positive, which means that the gain will not reduce as function of frequency and hence will not even cross over. Therefore, we need alpha to be greater than 0, and the smallest value that alpha can assume is some number which is approximately equal to 0, but actually slightly greater than 0. So, this is the minimum value that we can permit alpha to assume, because if alpha assumes values less than 0, then we are in real trouble, because our gain characteristics will not even reduce from some value above 0 dB to some value below 0 dB. In order for gain crossover to happen, we need the slope near the gain crossover frequency to be negative, which implies therefore that our alpha has to be necessarily greater than 0, and the smallest value that alpha can assume therefore is a value that is slightly larger than 0. So, if that is the case, if alpha is allowed to assume a value that is slightly larger than 0, that gives us an estimate of the maximum possible gain crossover frequency, and that is given by omega Gc max, and that is from this equation, from the equation within the red box. If we were to set alpha to be approximately equal to 0, so that we can ignore the term alpha pi in relation to the term Pm, we would get omega Gc max to be equal to A times cotangent of Pm by 2. So, what this analysis reveals therefore is that there is a maximum gain crossover frequency possible for a control system which has a non-minimum phase 0 in it, and that is given by this particular expression, A cotangent hyperbolic of Pm by 2. And I want to underscore that this is the first time in this set of lectures that you have come across this possibility that there is such a thing as an upper limit to the gain crossover frequency. In all the design that we have undertaken so far, both in the case of 2 degree of freedom control design as well as in 1 degree of freedom control design, we have assumed minimum phase plants, and for all such plants there was no such thing as an upper limit to the theoretical upper limit to the achievable gain crossover frequency. It could be as large as one would wish to be, and we can still achieve whatever phase margin we wanted to have for the closed loop system. It is just that we had to invest in a more expensive controller that had a much wider bandwidth. But here what this analysis reveals is that no matter how much money you are willing to pour in designing of the controller, there is nothing you can do to improve the bandwidth of the closed loop system. It is theoretically limited to the amount given by A cot Pm by 2. Now in this analysis we assumed that our alpha was approximately equal to 0, and that essentially implies that the gain margin for the open loop system in this particular limit, which gives us the maximum permissible gain crossover frequency, is actually equal to 0 dB. So we can extend this analysis in order to estimate the best possible gain crossover frequency when we also have specified a certain gain margin. So let us undertake this analysis next.